In this work, we have developed an immersive welding assistant to enable remote welding scenarios, thereby reducing health hazards for human welders, improve welding skill and productivity through simulation. The concept is explored using virtual reality and mixed reality. This assistant provides users with a head-up dashboard consisting of the real-time values of the critical process parameters such as welding current and voltage. This will help in improving weld quality as human welders usually have a limited visibility of the process environment due to the use of safety gear. To begin the welding, the user navigates to the setup within the virtual scene, adjusts the process parameters using the UI buttons, picks up the welding torch using the handheld VR controller and defines the weld path on the component. This weld path is transferred to the robot which replicates it in real time. It can be a set of waypoints or a continuous path for the robot to follow. Multi-modal feedback, that is visual, auditory and haptic vibration pulses, are provided during the interaction to reproduce the actual experience of a typical welding process. Thus, the intelligence and experience of the human welder is coupled with the stability and accuracy of the robot arm. Here is an implementation in mixed reality using the Microsoft HoloLens 2. The user defines the weld path using his or her fingertip on three-dimensional holograms of the components overlaid within the real environment. During the definition process, the generated path is clearly visible to the user. It is then transferred to and executed by the real robot. Calibration is done by using a QR code as a reference point and linear regression models between the coordinate spaces. Here is a schematic of the virtual reality implementation. There are three interconnected spaces, namely the user space, where the user interacts with the HTC Vive VR system, the virtual space consisting of the digital twin built with Unity 3D, and the robot space consisting of a tabletop Dobot magician arm representing the welding robot, a sketch pen end effector representing the welding torch, and the lines drawn by this pen representing the weld. The virtual scene consists of scaled models of the components placed and positioned in exactly the same manner as the real setup. The top edge of the workpiece table is used as a common reference point for mapping between the real and virtual spaces. The mapping is obtained by using a linear regression model between the respective coordinate axes. Comprehensive user studies were performed with the path definition task to compare virtual and mixed reality interactions. Participants defined a typical weld path consisting of arcs and straight lines with their hand movements. The defined user paths were then sent to the robot for execution. Quantitative parameters such as task completion time and accuracy measures, qualitative parameters such as NASA TLX and SUS scores, and physiological parameters such as brain activity with EEG and ocular parameters with eye gaze were measured and analyzed to explore the suitability of these interfaces for remote welding scenarios. Thank you.
In this work, we explored augmented reality and deep learning based system for assisting assembly process. The motivation of our work is, in industry, worker need a decision support system to instruct them when that lot size is small and many variants in the manufacturing process. So we developed mixed reality based system to give instruction to worker in 3D instead of 2D display or paper based form. This is our proposed method. So at first, user entered the IP address to make that communication between that server and HoloLens. Then user have to scan our UR marker to register that origin between that HoloLens and real world. Then user have to click the picture with the help of our eye gaze. When the user in correct position, eye cursor color will change to green. Then user download this image. This image input to that our YOLO algorithm. YOLO predicted each and every object position with respect to marker. Then this information send it to the HoloLens to render the holograms. Then user click that next button in the UI to get the instruction. So when the user click the next button, one object color will change to green, which will indicate that object which is going to pick up next. And also we are tracking that sequence of the task.
Check all that, please.
When the user making that
Check all that,
any
please.
error,
Check all that,
our
please.
fault detection algorithm
Check all
show
that,
that
please.
error message as an audio signal and also text message. We are using two arrows to give the instruction to the worker. Yellow arrow which will lie on the ground. The tail of the arrow will indicate that object which is going to pick, and tip of the arrow will indicate the where to place. And also in pink color arrow which is move with that eye tracker, which will indicate the position of the object which is going to assemble next. And also we are rendering that final step of that each and every assembly task. Our fault detection algorithm based on two factors. First one is that position of the component and position of that thumb and index finger. Next one is that difference between that size of the object and distance between that thumb and index finger. Then we conducted user study to evaluate that effectiveness of the multi-modal user interface. We are changing that arrow size and also display effect. With the help of this, we created 4 methods. We add one more method as a baseline method. From the study, we found that using the blinking effect, irrespective of that arrow size, it will reduce the task completion time. Then we conducted another user study on shop floor worker in the manufacturing center, and we asked a list of questions to them. From the study, we found that using different color and arrows, instruction can be easily perceived by that worker, and also they can clearly distinguish and a real and virtual object when we are in the HoloLens. The conclusion of our study is we proposed a regression based mapping method to render the holograms, which resulted in a mean mapping error of 1.8 cm. We also evaluated the proposed multi-modal interface using 2 user studies, and we found significant improvement in task completion time. From the second user study with the actual shop floor workers, we inferred that they could follow the provided instruction effectively, and they felt that the proposed interface provided better awareness of the assembly task. Thank you.